Here we are, core concept 5, and this is probably a subject, I would say, a topic which can have its own playlist of I don't know how many ever videos. It's a very, very sophisticated, I would say, topic. You see it in physics, you see it in different parts of physics and heat, you see it in motion, you see it in chemistry, metallurgy. A lot of people study it, and that is really friction, right? So it deserves its own video. Friction, okay. Deserves its own video. But what I'm going to try and do here is give you an idea of what friction is, hopefully allows you to intuit a little bit, and then try and translate this into some kind of mathematics, bring in a few variables, and hopefully we will figure out how they get applied into everything else we've studied: force, velocity, power, all of those, right? So let's start with what friction is, right? So friction, you could very simply say, is the resistance to motion right between two surfaces that are in contact with I've provided a very, very simple view to this, right? And I'll try and maybe use a couple of tiny chalks that I have here. And if these two were together, for some reason, forgetting the effect of gravity or anything like that, if I just held it, they're stuck to each other. They don't want to move unless I have an external force that pushes against them. And I'm trying to push a little bit, it's not really moving, they're held. And then when I push them, they actually move. And if I continued that movement, I don't know if you can observe, but actually I have these chalks losing out a little bit of material, right? So friction is that inherent property, and it's not unique to one object. It's what happens between the two at the surface where they meet, right? It's resisting motion to some extent. And that's why I gave you a very simple definition of what friction is. And what will we kind of study about friction? I think we will kind of get an overview that friction typically, it's not a fundamental force, right? But it's a resistance, and we'll explain that. It's not a fundamental force, it's reactive. It's not fundamental. Meaning you only realize friction when there is another force. Otherwise, you wouldn't really realize friction, because an object at rest continues to stay at rest unless acted upon by another force. If there was nothing else, if there was no gravity or anything, I just left them like this, nothing would be acting on them, and they would really not have the need to move against each other, and you wouldn't realize friction, right? Friction is not fundamental, it is actually reactive. Another area that you might want to think about is what happens due to friction, right? It's there everywhere. It's why you can swim, it's why you can walk, it's why a car can drive, brake, all of it happens because of friction. It's also, as you saw here, it is, right word, it causes degradation, right? So you can see that surface actually begins to lose some material and it causes heat. So some of its properties are different terms I use. I'm going to use the word degradation. Here is the result of friction. It also causes heat. And that classic example, take your palm, rub it, and you will realize that it is getting warmer in the area where you rub your palm. And that is also a result of friction. Let me go to one more area of friction that you might want to consider, and that is probably important because we will elaborate this in a little more detail, right? And I'll state this as a concept called, and write this as, just for simplicity, the coefficient of friction. COF for short. In many places I will just write COF. And it is denoted by the symbol mu, Greek alphabet mu. And this is really dependent. What is it dependent on? Depends on the materials. There's a lot more that goes into this, and that's why I mentioned friction is studied by those studying chemistry, those studying fluid dynamics. They all study them because there are other variables. If you make an object very, very cold, for example, you might have seen in extremely cold temperatures, try and hold on to a piece of metal, you wouldn't be able to take your hand out of it. Suddenly the adhesion increases. If you had extremely well polished surfaces, or the act of polishing a surface is really removing the little bumps on it and clearing it up so that it becomes smoother. But if you had two objects that were similar, they tend to have a higher resistance to motion because at a molecular level of that surface, their molecules seem to like each other, or you're similar to me, they want to stick together. So there's a lot of things, and it's really friction, coefficient of friction kind of relates to that system. So it's surface A or surface of material A, surface of material B, the temperature, other variables that might come in. Once you get it moving, sometimes it's a lot easier to move certain objects. The initial push needed to get them to move, so that initial friction, static friction if you will be higher. So those are some of the things that you might want to remember. But for simple terms, depending on the material, right, there is a coefficient of friction. We'll talk a little bit in detail about that because this is important. You'll find problems where you're given a coefficient of friction and you'll have to do something with it. And then finally, we have the force of friction. And what you will see me do for almost all cases is use F with a lowercase f as a subscript and denote a vector of this form. Okay? This is really where the magic begins, right? This is what we start using when we want to do problems and things like that. So I'm going to now bring in an example just to illustrate this, so you have a conceptual idea of what I described here. Really, I'm not going to talk much about reactive and fundamental forces, degradation, heat generation. We won't go into that for now. If we need to revisit friction in greater detail, we'll probably put something in the advanced area where we'll speak. Like I said, it's a topic I can go on for about 7 or 8 hour long videos, right? So let's go into the basics of what I want to show you. So here I have my tablet, and let me just take this. It's a very smooth surface, it's glass, and here's a bottle. It's an empty bottle. Let me finish though. It is truly empty, I think. Yeah. So it's extremely lightweight. So it's a half a liter bottle, so it's been half a kg when it was full. Super light now, barely a few grams, and resting on this horizontal plane, which is also smooth, fairly smooth. You might want to describe this as a plastic on glass scenario. It's stationary, right? Forget about the effect of gravity here because we're only considering horizontal motion. And let's just see what's happening. I'm going to give it a very, very mild touch, a very mild touch. And it actually, I can get it to move at a very, very mild touch. Maybe the better way to do this is if I use my chalk. There's a tiny nudge. Okay, it begins to move. I can get some movement on this. But now, we do this. I'm going to flip this over. And here I have, what is this material? I think this is probably some other plastic, right? And maybe it's resin or something like that, right? Or polyester, some other synthetic material. And now I'm going to try to do the same. It takes a little more effort, but I am getting there. I can move it, right? You're with me so far. So a little bit of effort, I could get it to move, but there was still some effort needed, right? It was just there, like there, it isn't moving, and then slightly, and then moves, right? I'm going to illustrate this now. Here's a full bottle. It's half a kg now. All right, now you sit there. Okay, he doesn't want to move. He doesn't want to move. Come on, you do it. Move. Nope, doesn't want to move. Increase. Nope, doesn't want to move. No, come on, come on, come on, come on, come on. Some more, some more, some more, some more. Oh, got it to move. Tad bit. So you see what happened. For that tiny bit of force, there was something that was pushing back. That's why this wouldn't move. As I increased the force, increased, well, no, not really. My finger's moving across the chalk. No, not really. It's not even moving. I'm gonna use my thumb now so that it doesn't resist. Okay, now, come on, come on. And I got motion. Okay. And I did that on purpose because what I want to illustrate to you is this concept of the force of friction. Now, one of the things, and it's very intuitive, you might have observed, and I'll draw a simple graph here just to drive home the point. If S was my displacement, an object moving, and I have force here, at a very tiny bit of force, whatever that force was, maybe it's 1 Newton, I got no displacement, right? Think about that half a kg bottle sitting. If I upped it a tiny bit, my finger, maybe at 2 Newtons, my fingers were actually moving, but the chalk was not able to get past. It was literally that the chalk was slipping between my fingers because that something was resisting the movement. Put my thumb in and then I upped the force a little bit. When I upped it a little bit, somewhere there, I began to record displacement. So I actually was able to see some displacement moving. There was some value of displacement coming up at that force, right? I'm going to try to say that this, and I'm going to call this here as, and I'll mark it with this color, where I got displacement. If I said that was F, let's say max, M-A-X, okay? This is just me writing a force, defining it as F max. what you saw that my force of friction, my frictional force was just under F max. Because at F max I got motion. So my frictional force, and it was less than F max. Perhaps, make it here. I wrote what happened here was when I had this 1 Newton or 2 Newtons, nothing was happening. But obviously there couldn't have been an F max pushing back because then the object would have moved. So friction, the materials were giving me that resistance, that reactive force and it was, when I gave it 1 Newton, it gave me 1 Newton, there wasn't a movement. When I gave it 2, it gave me 2 back, so there wasn't any movement. But as I approached F max and I touched F max, moment I beat F max, the bottom moved. So at all times, this force of friction would be less than or equal to F max, and right at just above F max, the bottle moved. So the frictional force is always there, just under a threshold, and it could be 0. If I was not pushing, there was no frictional force, right? When it was just a tiny push. But clearly, we also noticed that the lighter bottle just moved much easier, right? The lighter bottle didn't seem to struggle at all. This lighter bottle, here, all right, stay there, bottle. This lighter bottle didn't struggle at all. It actually just was quite easy to get the lighter bottle to move when the mass was negligible. So clearly, there is so how do we do this? Let's say that was my horizontal surface, and that was that bottle of a particular mass. When I applied my force this way, frictional force was the reaction that it gave me in this direction. It reacted. But now that I know that the heavier the M, or the more the M, that frictional force threshold was higher. So in some way, and let's say, what does M do? M is actually pushing down on the surface using the equation m times acceleration due to gravity. Which means Newton's third law would tell us that there is another mg acting this way. Now I'm going to call this mg as the normal force, normal as opposed to parallel to the plane. Normal to the plane is perpendicular. In the direction of the plane, it'd be along the plane. This is perpendicular. So there was this reaction force. So if I now take these two concepts, I can actually say that my frictional force in some form was proportional to the normal force, or a force that was normal to the plane of the surfaces that made contact. the plane of the contact surface. Hope you're with me so far. So I know that there is a value below which it can be zero, but I can get to that point, and I'm going to define my frictional force at this point here, saying this is the force of friction that causes a move, right? So instead of now saying this is F max, I'm just gonna say here, right, the force that will move. So I'm gonna say, if I say I want to define my frictional force at this point, that absolute bit of force that will cause the object, this is F, that will cause the object to move, right? Below that, there is no movement, because you can see here, frictional force is allowed to go to, it can go from zero to something, but at that point, it will just begin to move. And I found out here that, look, there is a positive correlation. But clearly, glass and plastic, easier. That polyester and the plastic, harder. So there was that dependency. It's all dependent on the surfaces, and that is where the dependency of materials come in. And typically, you would see this equation, and this is the key: friction force, and write the whole thing in green, would be equal to the coefficient of friction times the force normal to the plane of the contact surfaces. So if that's the contact surface, this is the force normal to it, and that would be your key relationship. Okay, I hope you're with me so far, right? So I'm now basically saying I have this reactive force that could be zero, but then it can go up to a particular value, and I'm defining that value. If you somehow mean that, if it's like saying I'm going to say my frictional force is equal to F max, right? Because below that, I'm really not interested. Let me then take you to another interesting problem while I have this here. And this is something I'm going to explain to you, again using this example. All right, it's not moving. Oh, and then it just moved, right? It's that bit that just took it there. All of the resistance that this surface delivered to me, I don't say object, but the surface, the contact surface delivered to me, all of that was when there was no motion. So what I will do now is I'm going to just denote here the concept that because it was no motion, it was static, and that means the coefficient was also a static coefficient. It was the static coefficient. You may ask why? Because once I get that motion, it's not moving, okay, let me do this, not moving, upping the force, it moved, and then I'm moving. But as soon as the force goes away, it stops. There is a force, and it's, say, slipping along in a constant velocity. If velocity is constant, you would say, well, there is no force. But the moment it was moving, there was still friction because I took my force out and it stopped. And that means there is also a kinetic friction. When there is motion, that's kinetic, there is a kinetic friction. But we'll get to that in a second. For now, this is the key relationship. The frictional force is equal to coefficient of friction times normal force acting along the plane, perpendicular to the plane. And for an object at rest, frictional force static is coefficient of friction static times the normal force. Hopefully you're with me to this. I'll take this out and I'll start developing a little more on this concept of static and kinetic friction, right? So I'll first address, I'm just going to give you the view on kinetic friction and what it means to us. So let me take this out. I'll keep this picture here. Okay. Now let's just say, if this was the case here, and I was applying a force F, that's just my force. Obviously, if it's in motion, F and frictional force, F subscript F, they all stay balanced. Everything is balanced. If I drew a free body diagram of the object, the free body diagram would basically have one force, another force, they're all vectors, and you can see this, the object is in equilibrium, right? So this would be m times g, this would be m times g, this would be my force in this direction, and this would be frictional force, and you would say F is equal to, because they're vectors, I'm just going to say here, or better still, magnitude of F is equal to the magnitude of, right? They are in perfect balance. A free body diagram, remember that there are some questions that often come up and says, draw a free body diagram representing forces. Really what they mean, right? I've taken this to kind of demonstrate it, but let's just, okay, small digression, but let's go back here, right? So this was there, right? Perfect. I got it to move, but then I kept a force on so that it kept moving. And if it moved at a constant velocity, you would always argue saying, well, constant velocity is no force. But the moment I took my hand off, things changed. So what is happening is, if this object was moving, and I'm going to extend this here, if this object was indeed moving at a constant velocity, let's say we move it to here, at a constant velocity v, forget about initial, final, if it was moving at a constant velocity v, you might say, well, hang on man, this just doesn't make sense. What force? Well, there's always friction here, so I could always say it's going in that direction, so the object moves in, as you look at it, it's from your left to right, right? The object is moving that way. Friction is the reactive force. So friction acts this way. Constantly, there is a force of friction. If only the force of friction existed, the object would move this way. Now, you could say that, oh, there is that little mg part here. Well, there is the mg part here too. But it was moving. At constant velocity, the net effect of the forces in this plane are zeroed out. So that means that force from my finger to keep that bottle moving was the force I applied, which is F. You could say F is equal to F friction, and the object stayed. Okay. Now, if I told you that in this state of motion, these two objects and this surface of, say, rubber and, or resin or polyester and plastic had a coefficient, chalk dust, had a coefficient of friction, but this time it would be kinetic friction because I'm moving. Then you could say that, so your frictional force in motion, I'm going to now use this parentheses K is equal to the coefficient of friction kinetic K times mg. That's the normal force, right? So I could develop this equation using that same principle, that frictional force having been related to the force normal to the plane, and that relationship is material dependent, or rather surface dependent, because if you had a rough surface, it'd be different if it was a perfect surface, and problems that you get often just assume it's a smooth surface and they give you a coefficient or ask you to calculate a coefficient, you just calculate it straightforward. That's the force, okay. So that means to keep that bottle moving, I was providing just that tad bit at this point. Well, if I was providing something greater, well, then the object would accelerate, isn't it? Because if there was a net force here is zero, because F that I provided, the magnitude of F, minus the magnitude of the frictional force vector is zero. The vector itself is in opposite direction, so it was F is equal to negative. Now, if I was writing this in a vector equation, I would just say the force vector is equal to the negative of the friction vector. So the net force was zero. So this is interesting. But what can we do with this? Well, if I know this, and remember, we talked about a few interesting things. I can determine, if I was having an engine that was powering this motion rather than my finger and, my arm and my body or my muscles trying to do it, if I had an engine that was doing it, there is something I could have done. If this was the force that was acted upon, and I knew velocity, if we learned from our previous lesson, power, if you remember, power could be written as force times velocity. Ta-da, I can actually figure out the power of a device required to push something at a particular velocity against the surface if I knew the coefficient of kinetic friction and the mass of that object. I can determine the power, because really knowing the force does me very little, right? And if I knew velocity, what do we know velocity as? Distance over time, or displacement over time. If I knew a value of time based on what the displacement was, I could then say, remember, force times displacement would also give us work done. Of course, it's just work done is just nothing but power times time, because if you remember, power is the rate of doing work, or it could be force times displacement. So, just a few things that you can develop on by understanding friction, and this is kinetic friction. So now let's get to the interesting part. You ask, okay, so what is this coefficient of friction? You keep bringing that in. Well, the coefficient of friction, again, material dependent, depending on surface, so wood on wood versus glass on glass versus sandpaper on sandpaper, ice on ice, or, glass on ice, all could be different. And how does one get to understanding coefficient of friction? It is experimentally calculated, really, but in order to do that, let's maybe we'll keep this picture here, okay? Maybe we'll keep these pictures here. Let's do something a little more fun. Let's ask for a box of coffees. All right, let's try this. Okay, it stays there, right? Here's my box of coffee, stays there. Obviously some friction. I'm gonna tilt this. Now watch what happens. I'm tilted. Tilted, nothing's happening. This is, what is this? This is like 250, what is it? Oh, wait a minute. 320 grams. Okay. It's got a mass. We know the mass. Tilt, 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 tilt. Wow, they're holding together. It's whatever, resin and paper. But wait. Is anything gonna happen? Is anything gonna happen? Whoa. Nothing. Come on. There was that tiny piece, somewhere there. Oh, where it started moving. Now this is an interesting part, right? Now let's go back to, and remember, this becomes relevant because we've done a lot of discussions on all of this when we did vectors and resolving forces, and you see how they come together. There's my box. I'm not going to draw a free body diagram here. You can figure out how to draw a free body diagram. I did explain that this box, and give this coffee box a little color, right? Just so you know. This coffee box had a mass of 0.32 kilograms, okay? What might be going on? Well, let me draw my horizontal plane here. There is an angle, theta. What might be going on? We'll draw whatever happens during this box. So I'm gonna just assume this is my point of interest, right? This is my point of interest here. So for purposes of this calculation, I'll just say, actually, you know what, maybe my point of interest should be here, just to simplify it. So I'm going to draw this line here with an arrow here, okay? This is the force of gravity. We know G. I'm going to extend that force here, just so you see what's going on. I have a right angle triangle first, that's great. Now, I'll just draw that there, just as an example, right? I can resolve them into, because the motion and the displacement vector is along here. I can resolve that, if this is theta, I can resolve a downward, along the incline, I can resolve a force. I can also resolve the force along this direction. With me so far? And if you know your angles, you would say, if this is theta, and maybe my drawing is not perfect, this is theta. Yeah, come on, don't do that. I could say this is also theta. This is 90 minus theta. Okay? We know from resolving forces that there is a downward force that gravity is causing. Okay? There is a downward force, and this would be, need more space. If this is the force, that's theta, this downward force would be, this downward component, if you will, would be mg times cosine theta. This component would be, so let me, how do we denote this? Let's just say downward, and if you, well, maybe not even downward, let's just give it the term F1, And here we see the component F2 is mass times gravitational acceleration times sine theta. With me so far? And I can now move this just to that point, right? So at all times when it was tilted, there's that, if there was only the F2, it would have slid straight down. Clearly it wasn't. There was constantly the force of friction pushing it this way. Then this is my frictional force, F. And as I increased it, mg sine theta kept increasing. Frictional force reacted and went up. You remember, frictional force went from 0 and went up to an F max. And in this case, as it approached that F max, got to that point where if just a tiny tilt above would mean I would have increased F2, because as theta increases, sine theta goes up. If you remember, sine 0 is 0, sine of 90 is 1. So sine theta goes up from 0 to 90. As theta increases, sine theta increases, and therefore this component F2 increased. And at that very moment of time, or that very precise angle at which my F2 was able to beat the force of friction, right at that instant, right, of equilibrium, if you will, I would have been able to say that my frictional force F was equal to the horizontal component F2 but I also know that frictional force F is, and I'm going to now say F2 is this, but frictional force F is the coefficient of friction times, again, static friction. I'm discussing static friction here because there is no movement. To make it clear, I'll just say static, but problems often, again, you might not see the word static being used, but it's static friction coefficient times F1, the normal force, because whatever comes down here, Newton's third law provides a pushback of exactly the same value. Okay? Which is what holds the object in equilibrium. In equilibrium, these are all just the way it is. A tad bit of theta going up increases F2, a tad bit balance is lost, and the object begins to slip. So at that instant of final equilibrium, this is what I get, is equal to m times g sine theta. I'm going to work the manipulation out, but you probably figured it because I could write mu static now as equal to m times g sine of theta divided by F1 is here. F1 is nothing but m times g cosine of theta. Cancel, 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 cancel. Sine by cosine, you guessed it, is nothing but the tangent of theta, which means I could write theta is equal to, some people call it the arc tangent, some people call it the inverse tangent. I want to just write it as tan inverse of theta, of mu. In this case, mu static. But if there was motion, it would be mu kinetic. Okay. If there was motion. And if it was motion at, you guessed it, constant velocity. Because at constant velocity, this force, there is no net force acting, right? If I have this object falling at a constant velocity, then we know that its motion is perfectly balanced with frictional resistance and gravitational, and the component of gravity pulling it down. You would have the exact same map that comes in and you could just write theta, but at that for the sake of static friction, this is also called the critical angle of friction. The critical angle of friction. Theta is the critical angle of friction. Some people call it the limiting angle of friction, which is the maximum angle which holds an object in place, or the maximum angle of an inclined plane on which an object does not move. A lot of these definitions that come in, but again, remember, they were all dependent on this factor mu, which is dependent on materials. So you'll find textbooks that give you examples of how wood on wood has a coefficient of friction of 0.6, and how steel on steel has something else, and tons of numbers. I can't memorize them. Most problems will give them to you or ask you to calculate them through this interesting manner. If you can calculate theta, you can calculate mu. That is how it is scientifically, or rather experimentally, established, and that's how people calculate them. Because we can measure angles very precisely using instruments, and then we can set it up in such a way where we can observe, where motion begins, and that very tiny, precise instruments can set motion up, and we can, basically have a steel plate and have a block of steel, and you measure its mass precisely, or the force to your mass, and you can do these calculations and get theta. When you know theta, you can do the arctangent or the inverse tangent, as different textbooks call it. I just like to use tan inverse to get you can get tangent of theta, and then you can calculate mu from there, right? And then if you've been given mu and you know the properties of motion, you can calculate the angle of inclination. I hope this is clear, because the same logic that I applied on the equation for moving something on a horizontal plane and then translating that to power would become applicable here. If this was moving at a constant velocity upwards, actually this is interesting. Here you have two possibilities that happen here. Let me go into that. I think this is important. I hope you're with me on this. You've seen how, and I brought the inclined plane really to show you how mu is calculated, right? Constant velocity, or at static, you can get mu using tangent theta, right? And that's how mu is determined. In your problems, usually you're given the coefficient of friction. Let me take this out and then go back to another interesting case. Now that we have the incline on, let's discuss the incline a little bit, right? And hopefully I don't make it very messy. Normally they do get messy. Actually, I'll take it all off and then just draw it nice and neat, so we have a better appreciation of what's going on there. I'm going to leave you with a concept really, rather than attempting to do any solutions here. I'm going to leave you with this idea. So there's my horizontal plane. There's my incline. And there's my theta, right? There's my box. That's my surface of contact. There's the mg component, the main mg, and from here on I'll just go easy. There's the reactive normal, mg cosine theta. Now where is mg sine theta? Well, mg sine theta is always going to be here. Okay? mg sine theta is always there. I am making this messy. I don't like that. I am making a mess. I gotta sort this out. mg sine theta. Hopefully it's clear. This is mg sine theta. Now, think about it this way. You could have the object moving downwards with constant velocity, because if it didn't have, if you just exceeded, if mg sine theta, if theta was higher, imagine what would happen. If theta was higher, the net force acting on this object, so friction is going to do this, right? So assuming nothing else, friction is going this way. So the force of friction, I'm going to write here. This is the frictional force, right? Object in equilibrium, right? Object in equilibrium. No movement. We know that when theta goes up, net force along this plane, and I'm going to denote that net force in this plane, and I don't know the direction. I'm just going to put it, the net force along this plane, I'm going to call this as F net. It's a vector, I don't know its direction, right? Would really be the difference between this and this. I could write this equation as is equal to the difference between, and you can see here, the direction of force of friction upwards subtracted by, or by, and I'm going to do this, right, mg sine of theta, not giving it an f value, but this is a vector now along the directions, right? So if mg sine theta went up, because theta went up, you can see that this becomes much larger, and therefore f net will appear negative, which means it is effectively in the opposite direction of friction. If mg sine theta was lower, you would see that doesn't matter, force of friction adjusts itself downwards, so F net will remain 0. But you could have an F net in such a way where that object is at constant velocity as well, right? If this object is moving at constant velocity, well, F net is 0. So once motion started, it would be the same, the problem statement would be identical. If motion started in this direction, downward direction, as mg sine theta went up, you would have F net in the direction opposing friction, so it would be downwards, and you would do the exact same calculations. You could identify work done, you could have those, but really you could also catch it at that point where you say, okay, there is an F net at which it moves, but after that, it's moving at constant velocity. Well, but then the moment you say that, you go like, but gravitational force somehow, this is acceleration, right? So this will, as long as it has a component, as long as this thing exists in some form, it will keep trying to accelerate, and that's spot on. So if you didn't have anything else holding and you passed your tipping point, that means this one's tipped just a little over force of friction, F net will keep increasing because acceleration due to gravity keeps increasing velocity, and you'll find the object speeding down. So the problem I'm going to give you is I'm going to say, okay, now I want you to make my object fall at constant velocity. It's going to fall at constant velocity, which means I need to always have a force acting here such that F net is 0. Otherwise, gravitational force will always keep it high. So if I gave in an additional force by myself in excess of friction, then I would be able to keep this system in equilibrium in moving in constant velocity. How would you calculate that force? And that's where you get to say, you develop that equation saying, okay, now that I have an F net, I can calculate this difference, but it's a constant velocity. So then I can say what is the power of that force. That's why power becomes important, because force itself is just mathematics in an exam problem. But in practical life, you need to get the power that is required for you to keep this object at constant velocity, sliding down at constant velocity, because left to its own accord, as soon as you get this one goes over friction, it's going to speed down. It's going to start accelerating down. So to keep it at constant velocity, so think about it this way: if you have an incline elevator or an escalator and you want to keep it in constant velocity, you need power. That motor needs power. Otherwise, you just have it race down. Now it becomes practical, and that's what we need. So remember the calculation. You would use the same thing: constant velocity. What would I need? Find out what kind of F net would be, comes into play. Multiply that with velocity, and you will get the power required. So same kind of calculation. So I thought I'd kind of go back and highlight this to you. If motion was in the opposite direction now, imagine you were going up this way, what would you do? Oh, this is interesting. If you're going the opposite direction, well, friction is resisting motion. You would think friction is here. So now you would have a case where your F net would have to go, you would have to be, in order to have movement in the opposite direction, your F net would have to be greater than the force of friction plus, and actually I would say the magnitude, because you're obviously in the opposite direction, the magnitude of this plus the mg sine theta. So if you were moving in the opposite direction, the frictional force would now act along the same thing. It works against you. That's where these problems begin to get tricky, right? So if you suddenly had a question saying an object's sliding down at a certain velocity, but now I want to take it up, make it move up, what am I going to do? Well, wow, I need to find out how much, and if the question is based on the power, hey, how much power does a motor need to stop it and turn it back? Well, then there you go. The moment my direction goes that way, friction just decided, till now I was working for you, now I'm going to work against you. Ta-da! And then you're going to start calculating these problems, computing these two factors together, and then say, okay, constant velocity upwards, well, that means I've beaten sine theta, and I've beaten the force of friction that's now acting in this direction. I've beaten the sum of those two, so I can have constant velocity in this direction. Okay, velocity times pi, and then you know the force, because it has to be equal with constant velocity. So I've equated F net to this value. So I calculated this by doing the creative manipulation of using mu of cosine theta to get this value. All of that to find frictional force of the surface, but now I'm adding the frictional force to the gravitational force component, and then saying that that's the force to keep this object at equilibrium at constant velocity, and then I know the force multiplied by velocity can get the power, and that's the power required by the motor to keep this block moving upwards in a constant velocity. Hopefully that is clear. So this is a very interesting topic. There's lots to do with this, but hopefully you've got the fundamental idea. I'm going to write that down again. Very important. Frictional force is equal to coefficient of friction times the normal force, or the force normal to the plane of contact. Very, very important. And usually most problems, unless you're doing friction hardcore as a subject, for most problems, they'll give you a coefficient of friction saying sliding down, and then they'll ask you to calculate other things. So really you'll stay within the realms of just using this. That is it for friction. I will probably provide another video continuing on 5, and as a checkpoint that includes several concepts that we've studied, and build in some friction, some elements of friction in it, just so you understand how to do these problems, tied to power, maybe kinetic energy, and other aspects of displacement and velocity. So I'll probably do that as a part 5B or part 5A, if you will, in another video where I'll go through a problem. But I do encourage you, now is a good time to open your exercise books. Pretty much, even if you're at the further mechanics of the A level, you should be ready to now go and start doing pretty much any problem in the first couple of chapters, or the first 3 chapters. You should be fairly good. And if you're in other high school physics streams, you are pretty much set with these concepts to start attempting problems. If you have something that's really exotic and challenging, happy to take that over. Right? I'll leave you with that, and good luck, and until the next video.